VLSos here. This is a video lesson on volume of revolution with a switching of a line, which means we typically revolve around the axes, either horizontal or vertical, to create a volume from a two-dimensional region. But this time we're going to move the line to be somewhere other than an axis, and then see how that changes the representative region and therefore the integral that we need to use to find the volume. I have a sample problem here. Find the volume of the solid formed by revolving the region bounded by f of x is equal to cosine and g of x is equal to -1 on the interval from negative pi over 2 to pi over 2 around y is equal to -1. And it's this last bit that we're going to revolve around a line that is not an axis that is the reason why this example is being given. So we're going to use the strategy before we jump into writing the integral to evaluate the volume is to visualize what's going on, visualize the region, try to visualize the three-dimensional solid that gets created by that region, and then the chances of setting up the correct interval will be a lot better. So I'm going to graph the region that is bounded by these equations by graphing each equation first. We have the cosine function. Cosine starts at its vertical intercept at 1 and comes down to a horizontal intercept at pi over 2, and if we go in the negative direction, cosine will have an intercept at negative pi over 2. So cosine is a sinusoidal curve, and it's periodic. It keeps going in both directions. But what we are focused on is the piece of the cosine function between negative pi over 2 and pi over 2. So that's it there, that positive region above the x-axis. I also have the constant function g of x is equal to -1 to constrain the region. The constant function g of x is -1 is a horizontal line at y is equal to -1. And now technically the cosine function will intersect this line outside of the interval from negative pi over 2 to pi over 2. But I'm not going to show those intersections. I'm going to place dotted lines to show the boundaries of the region given by this interval. What I care about is only the space in between these functions from negative pi over 2 to pi over 2, which I've shaded here. That is the region that we're going to revolve, and we're revolving it around the line y is equal to -1, which is also the g function. I like to use this symbol that looks like a circle in perspective to label the line that I'm revolving around. I'm revolving around this line here, y is equal to -1. Now that I have my region, I'm in the habit of forming the solid that gets created and attempting to draw it on the paper by imagining some point within the bounds along the function. It could be anywhere. This is a representative function value. And the representative slice of the region then is using that function value to find a vertical line within the region that represents any vertical line within my bounds. And with this, imagine the point and that line revolving around the line that I'm going to spin about to create a representation of the slice, or the two-dimensional region that represents the things we're adding up to create the volume. So again, this function value, I chose one arbitrarily, is going to revolve around this line here. So the function value on my paper is a little more than 6 boxes. So if it revolves around that line, I have to make sure to make those distances the same as best I can. And imagine the point, we have to get a three-dimensional perspective on this, is revolving around that line. And the point then makes a circle in the third dimension. So the entire line makes a disk, a filled-in circle. And if we can visualize this as a disk in the perspective of 3 dimensions, we have a representative slice of the solid that is being formed. To help complete the illusion of a 3-dimensional solid, I'm in the habit of doing the same thing with my endpoints. So we have function values at -π/2, and that function value will revolve around the line, creating a circle. And if we think of the function value then also representing a line, the entire line then revolves around to make a disk. It happens at this last function value. The point makes a circle. The line makes a disk, and these two disks are the ends of the solid that's being formed. The rest of the disks, I can't draw them all. It would blacken up the paper and be impossible to complete, but I can represent the other edge of these disks connected by a symmetrical curve that we used up here. This entire curve is revolving around and eventually creating the other sides of these disks. So if I attach these disks with a curve symmetrical to the top, I can complete what is hopefully the illusion of the 3-dimensional solid that's being created by revolving that entire function. And so this is not mysterious. We like to name these solids. So what kind of name would we give to this solid? It looks like a bead that's not hollow, that doesn't have a space for a string. It's solid all the way through. Or we could think of it as a ball that's been kind of squashed or distorted, or the sides have been kind of chopped off. I'm going to call this, and I'm going to darken the edges. These edges we're going to give the illusion that they're in back or behind. I'm going to call this a sliced ball. How do I find its volume? The volume is created by adding up an infinite number of infinitely thin slices, and each of those slices is a disk. So if I focus now on the geometry of finding the area of any disk, no matter where it is, then I'll know what to integrate. Disks are quite simply found, the area of a disk is quite simply found from the area of a circle formula, pi r squared. So if I knew the radius of these disks, then I'd be able to square it, multiply by pi, and find its area. What is the area of any one of these disks? Let's go back to the representative line that was the radius that created the disk when it spun or when it revolved. The length of this line is the sum of the function value that comes from cosine, but that's only the distance from the horizontal axis to the cosine function. I then also add 1, the space between the horizontal axis and the line that I'm revolving around. So that radius is cosine of x plus 1. And that's true no matter where I'm creating my disk. The equation for the radius is a cosine x plus 1. So it's the plus 1 that is the change that was made by changing the line of rotation from a typical x-axis to this line at y equals -1. No matter where you put the line of rotation, it's just going to include some extra thought about how to find the correct radius to create the correct geometry of the representative slice. In this case, we had to add this space to the radius of plus 1. Very often it includes some addition or subtraction. Now, with the expression for the radius of any representative disk or slice, I can find the area of that disk by squaring it and multiplying by pi. Now that I have the formula for the area, I have what we need to integrate. We're going to be integrating areas of disks. Those are the slices that we're going to sum up to create the volume. So the volume is the sum, or the integral, of all of these areas, pi times the cosine x plus 1, which is the radius, squared with respects to x. I have bounds of integration because I'm going to start creating disks at -pi/2, and I'm going to stop summing up disks once I get to the last one at pi/2. So the bounds of integration are -pi/2 to pi/2. And I'm going to speed up the process of now evaluating this integral, because the intention of this lesson was to think and visualize and set up the correct integral. But now that we have the integral, it's just a matter of using the fundamental theorem of calculus. A couple of steps I'll remind us of are making this a little simpler to integrate by bringing out any constants. In this case, pi can be brought out. It might be helpful to distribute the cosine x plus 1. If we do, then the integrand changes to cosine squared x plus 2 cosine x plus 1 with respects to x. And to give a final answer, if we were to find the antiderivative and apply the bounds with the fundamental theorem of calculus, we would come up with 3 pi plus 8/2. And if we approximate pi, then it's an approximate volume of 8.712. The focus is, when revolving around a line that is not an x or y axis, it's simply to slow down and draw the representative slice and think, how does changing the line change the value of the representative function or radius that I need to rotate? And it's usually pretty obvious that you need to either add or subtract a certain amount to then adjust the value that produces the area of the slice.